Hello everyone. So this is a continuation of solving for Couette flow velocity distribution, and I will just quickly recap what we started with in the class. So I first commented that equation of motion is a vector equation, so we will typically have three equations to work with. If I'm working, for instance, in Cartesian coordinate system, then I'm going to have x, y, and z coordinate equations. If I'm in cylindrical coordinate system, I'm going to have r, theta, and z coordinate equations. So you have a choice of using Appendix B5, which is Navier-Stokes formulation. Again, Navier-Stokes equation is equation of motion for Newtonian fluid of constant density, and this is the one that we will use the most in terms of shear stress tensor. So if your boundary conditions are expressed in terms of shear stress, or you need to solve for shear stress, this is the appendix you will be using. Appendix B6, which is Navier-Stokes formulation in terms of velocity, is the one where boundary conditions are done in terms of velocity. So for instance, this is the Appendix B6 for cylindrical coordinates. Okay? Now, if you watched my extra moves, this is basically what is a material derivative of velocity. So just at this point, just use it. So this is rho times all of these partial derivatives of v, and minus this is the component of the gradient of pressure in our direction, and then we have the component, this is the shear stress components, which is basically plus mu Laplacian of v, r coordinate of it, and plus rho gr. So what you're really tasked with is taking the appropriate equation that you need to solve for, and then looking at all of the terms that cancel out because of the assumptions. So when we had the Couette flow, which is our flow here in a viscosimeter whose outer boundary at radius uppercase r is moving at constant angular velocity omega 0. That means, so this is my omega 0. That means that my linear velocity v theta, which is the one tangential to this, is equal to omega 0 r. Okay? And the inner boundary at kappa times, this is Greek letter kappa times r, is equal to 0, because this is a fixed or static cylinder that I'm tasked with solving for a flow. And as we commented in class, and this is what we spent today the most of the class of, is basically looking at the theta equation. So when you look at the theta equation, this is this one. And again, we have to look at that one because we're looking for v theta. So I'm looking to balance theta momentum. Then most of these things will disappear. Time derivative is 0. So I'm going to do it right now. So my time derivative is 0. Basically VR is by assumption 0, so this disappears. My theta derivative, so my v theta is by assumption of r. Vr is 0 and vc is equal to 0 by assumption. Then this is 0. This is 0 as well as this. And VR is 0. So what I have on the left-hand side is rho times 0. That has to be equal to, I assume that pressure does not depend on theta, because there's nothing really to change the pressure in theta direction. So basically, I'm going to have minus 0 plus mu. And then, so this is, but my theta is really non-zero, is this component. And in r direction, because of the radial changes, right? So only in radial and z components I expect changes in theta. Now, if I look at the rest of this equation, what do I have? This is a function of r, so all of this exists just fine. So that I cannot reduce. And then this is 0, this is 0, and this is 0 because VR is 0. And I don't have theta component of g, so this is 0. So this is all that survives. And this is what we worked with today in class. So this is B, 6, 5 after canceling terms. Excellent. So this is what we worked with in class, and we came up with this general expression for v theta of r when I integrated things. And these are the boundary conditions. So inner cylinder is static, and the outer cylinder rotates with constant angular velocity. So when you plug in these two and find what C1 and C2 are, then you will get, hopefully, that V theta of R is omega 0 over 1 minus kappa squared, R minus kappa squared, R squared divided by R. So this is my expression for V theta of R. So we have solved for V theta for R of R by looking at theta equation for my Navier-Stokes. Now your assignment, in addition to this, so basically this closed form, so we have just found that. And what's interesting is that V theta does not depend on viscosity. It really just depends on omega 0 and then kappa and R, right? So it depends on R, of course, but the constants that play a role in, so R and then constants omega 0, R, and kappa, okay, which come from my boundary conditions. Now I'm also asking you to simplify R equations to obtain pressure dependence on V. So R equation is this one. So I hope that you can basically solve that, and I will just give you the results that you need to get, but basically what you would get, oh, apologies, so this is, yeah, this is pressure dependence on V theta. So basically what you should get when simplifying the C equation is that minus rho V theta square of R is equal to minus dp dr. And this is a function of R. I could integrate this too, but I'm not going to calculate that right now. But that's my pressure response in R direction. And then this D, when I simplify Z equation, I should get, so this is the Z equation, B6, 6. I should obtain that 0 is dp dz plus rho g. Okay. So from this, you can actually, these are actually, we're not going to solve them, so pressure is a function of R and Z. Excellent. So now question is, what is the force exerted by the fluid on the outer cylinder? And I would like to first express that in the, so I will now switch to looking at the force on this outer cylinder. So this outer cylinder is the one that rotates. So what is the force that we're looking at? We have theta, V theta is non-zero. So we will have theta momentum transfer across our plane. Okay, of course it transfers on across all of the planes, but I have the solid surfaces are aligned with either r is equal to r or r is equal to kappa r. And those are two planes in our theta z coordinate system. And I have aligned my coordinate system with these solid surfaces. So that makes it easier for me to calculate these forces. Now we will remember that basically that the force that I can look at the theta momentum transfer across these planes. So typically I look at it in coordinate direction. So technically this fluid in the lower r coordinates, so my r coordinate grows in this direction. So if I look at this surface, the fluid on the lower side of r exerts effective force on the fluid in the upper side of r, which is basically where my solid surface is situated. And that's essentially expressed by tau r theta. So basically that is my shear stress, because I can look at my tau r theta both in terms of the momentum transfer from this side to the other side, as well as the effective force that this side exerts on the basically plane r is equal to r. Okay? So essentially, by definition, I need to give myself another slide, I believe. Yeah, I need another slide. Keep. So let me just give myself an empty slide. And let's just be cautious here and do two. So my tau r theta, I should use the color that I used for it, so I'm going to continue with this color. Tau r theta, that is force in theta direction exerted by the fluid in lower R onto the fluid upper R across our plane. So basically, what I'm, and this is normalized, of course, by the area. This essentially is a normalized. So that's basically what I'm looking for is tau r theta at r is equal to r is my force on a fluid element or a solid surface. R is equal to r, solid surface area element. And that's precisely what I'm looking for. This is my outer cylinder. This is my outer cylinder. Excellent. Now what I will look up to is how do I get tau r theta? Well, we know that we have to look up in the appendix how to calculate tau r. I already have v theta of r. The question is, what is my tau r theta? I will go to my cylindrical coordinate system expressions, and I will find out by B111, that my tau r theta, which is the same as tau theta r, is equal to minus mu, and then r ddr v theta of r plus 1 over r dvr v theta. Now I know that my VR is 0, so this element, this part is going to go to 0. I know what my V theta of R is. We have computed that. Okay. So my V theta of R, whoa, apologies. My V theta of R is equal to omega 0, 1 minus kappa squared, R minus kappa R squared R. So my tau R theta at any radial plane is equal to minus mu r times ddr of this expression divided by r. So that's going to be omega 0, 1 minus kappa squared, 1 minus kappa squared r squared over r squared. So when I take the derivative of that, this first part is a constant, the derivative is 0. So what's left is, and there is a minus mu r here, ddr of essentially 1 over r squared. So we have ddr of 1 over r squared. This is r to the minus 2. So derivative of that is, can you tell me? Wait a moment and find it yourself and then plug it in. Okay, because the first part is the constant. And when you do that, I want you to derive yourself and basically obtain a form of tau r theta of r. So I don't want to derive everything for you. Find it. And then the last piece that we need to do is we need to evaluate this on r is equal to r. Okay. So basically tau r theta of r is force on the surface element. And it's basically of outer cylinder, and it is constant on all the outer cylinder. Now this is really just the force magnitude. Its direction is in theta direction. Okay? So technically, the proper expression for the force is tau r theta of r times area of the element is r d theta dz, and its direction is the delta theta, which this is actually, so this is area element on surface r. This is shear stress expression at that plane. So shear stress times area gives me actually the force, and this is direction and tangential to r is equal to r, and it's in theta direction. So it's the same direction same direction as my velocity, v theta. Okay? So it's in theta coordinate direction. So in order to get the total force,